Hello, we are here with one more lecture session on multivariate calculus integration. In the last lecture session, we had started discussing line integrals of vector fields. We had seen that the line integral or curve integral of the vector field f along a curve C from A to B is defined as the limit of a sum as limit n tends to infinity summation f of xi I dot delta Ri, where I varies from 1 to n. Here the curve C is essentially divided into n parts by some points as P0, P1 up to Pn, and psi I is a point in an arbitrary interval Pi minus 1 Pi. And this line integral is denoted as f dot dr along the curve C from A to B, or just f dot dr along the curve C. If the curve is a closed curve, we know that the endpoint and the starting point coincides in this case, and now the line integral is denoted as f dot drc with this notation for a closed curve. Further, in Cartesian coordinates, the line integral f dot drc will be given by p dx plus q dy plus r dz over c, where p, q and r are the components of the vector function f in the x, y and z directions. So, let us now investigate what do we mean by path independence of line integrals. Now, of course, as the term suggests, it means that if we evaluate line integral from one point to another along different paths, the line integral will have the same value. This is essentially the meaning of path independence. Now, we have seen in the last session that normally line integrals do depend on the path or the curve along which we integrate. But there may be situations when the line integral is path independent. And when is that? So the line integral of a vector function f given by pi plus qg plus rk is said to be path independent even only if p, q, r are continuous functions in a domain D, and if there exists some scalar function u, function of xyz in the domain D such that f is equal to grad u, or that essentially means del u del x equal to p, del u del y equal to q, and del u del z equal to r. And in this case, see that the line integral along the curve C from A to B is just given by ub minus ua. That is the difference of the value of the function u at the points B and A. Why this is so? We can easily observe that since P is del u del x, Q is del u del y, and R is del u del z, P dx plus Q dy plus R dz is nothing but du. And therefore, as we integrate du, we just get u from the point A to B. So this gives ub minus ua. We may also note that this result for line integrals is analogous to the fundamental theorem of integral calculus for functions of one variable. We now again move to define conservative field. But before that, note one thing, that if the line integral is path independent, then for a closed curve, the line integral will be nothing but 0, because for a closed contour, the starting point and the end points coincide, and therefore it is nothing but 0. Let us now define conservative field if the line integral of a vector field f is independent of the path of integration. Then only we say that the vector field f is a conservative vector field. So let us now see a theorem which gives a necessary and sufficient condition that the line integral of a vector field f with continuous derivatives is a conservative field, and that is nothing but that there exists some scalar point function u equal to u of xyz such that f equal to grad u. We can easily understand this because a conservative vector field means nothing but that the line integral is independent of the path of integration. And we have just now seen that the condition for the line integral to be path independent is nothing but that there exists a scalar function u such that f equal to grad u. And this scalar point function u is called the scalar potential of the vector field f. So now we have a test for a conservative field which will be very useful for doing problems. The line integral of a vector function f equal to pi plus qj plus rk is path independent, and this is equivalent to that the vector field is conservative even only if rot f or otherwise curl f, which is given by this 3 by 3 determinant ijk in the first row, del del x, del del y, del del z in the second row, and the components of the function pqr in the third row is 0. So therefore, this is our condition for a conservative field that the curl f should be equal to a null vector. Next, we see another very important fact, the physical significance of line integral. Work done by a force. Now we know from our knowledge of physics that work done by a force in moving from a point to another point is nothing but force into displacement. So here we can easily see that the work done by a force F on an object moving along a curve CZ will be given by the line integral F dot dr along the curve C, where F is the vector force field acting on the object and dr is the unit tangent vector. So the elementary displacement along the curve C. So finally the work done is nothing but the line integral F dot dr along the curve C. And note that if the vector field is conservative, then obviously the work done in moving along a curve from point A to point B will be just given by ub minus ua, where u xyz is the scalar potential of the field. Let us now move on to problems. Find the work done by the force field F of xy equal to xy, x plus y, on an object moving from the origin O, 0, 0 of course, to the point A given by 1, 1 along the path C, where first path is C is the line segment y equal to x, and the second path in the question is the curve y equal to root x. So let us try to work out the problem. First for the line segment y equal to x. So the work done is, we know, nothing but F dot dr. In Cartesian coordinates, it's going to be p dx plus q dy along the curve C. In this question, p is xy and q is x plus y. So we have just substituted. So this becomes xy dx plus x plus y dy. And now, since we are integrating along the curve C, which is nothing but the line segment y equal to x, so let us substitute that. So we have put here y equal to x, so this is x into x dx plus x, and dy is of course dx. Also, as we move from the origin 0, 0 to the point 1, 1, x of course vary from 0 to 1. So this is nothing but x square plus 2x dx. As we integrate, it's x cubed by 3 plus x square. You put the limits from 0 to 1, you simplify, the answer is 4 by 3. Next, let us compute the work done along the second path, which is going to be y equal to root x. So once again, the formula for the work done is the same, integral f dot dr or p dx plus q dy. But now y is replaced by root x. Here also we substitute root x. And of course, if y is root x, dy will be given by dx by 2 root x. So as we simplify, this becomes x to the power 3 by 2 plus x to the power half by 2 plus just half dx. We integrate. So this first term gives us x to the power 5 by 2 by 5 by 2. The second term gives us x to the power 3 by 2 by 2 multiplied with 3 by 2. And the third term is just x by 2. We put the limits. The answer is 37 by 30. So we observe here that the work done along the two different paths are different, which actually tells us that means this force field is not conservative. Let us move on to another example, and now we will take a conservative force field. So we have a question here now. Determine if the vector field f of xyz given by yz, xz plus 2y, xy plus 1 is conservative. If it is, find its potential. Also find the work done in moving an object in this field from 1 minus 2, 1 to 3, 1, 4. So, in order to test whether the vector field is conservative or not, we calculate the curl of the vector field. So, the rot f or curl f is here ijk, del del x, del del y, del del z, and the components of the functions are now yz, xz plus 2y, xy plus 1. So, as we evaluate the determinant, we get I multiplied with del del y of xy plus 1 minus del del z of xz plus 2y plus this unit vector j, del del z of yz minus del del x of xy plus 1, and the last term k multiplied with del del x of xz plus 2y minus del del y of yz. So as we evaluate this partial derivatives, we see this term gives us just x. This one again gives us x. So we have x minus x. Similarly, for the j component, we have y minus y, and the k component, we have z minus z. So we clearly see that the curl of the vector field is a null vector, and this confirms that the given vector field is conservative. So the next part of the question is that if the field is conservative, we need to find the potential. Now we know that if the vector field is conservative, then there exists some scalar function u such that f equal to grad u. So f dot dr, if we assume is equal to grad u dot dr, and we know that the components of grad u are del u del x, del u del y, del u del z, and the components of dr are dx, dy, dz. So we get grad u dot dr as del u del x dx plus del u del y dy plus del u del z dz, which we can easily see it is just du. And let us now use the expressions for f. So we put the components of f and dr over here. So we get this as yz dx plus xz plus 2y dy plus xy plus 1 dz. And if we look carefully, now see that we can write this as d of xyz plus y square plus z. Because d of xyz, see, it will give us three terms basically. Yz dx, this is here. Next, it will give us x z dy, this is again here, and dz xy, this is here. D of y square is 2y dy, and last term is dz. So from here we can now say that the scalar potential u is xyz plus y square plus z, plus we can have a constant of integration c. So we have obtained our scalar potential u. And we now know that for a conservative field, the work done is just given by the difference of the scalar potential at the 2 points. So it's just u 3, 1, 4, the final point, minus the value of u at the starting point 1 minus 2, 1. If you calculate this, you will get it as 14. So the work done in this case is 14 units. With this, we will close today's session. And in the next session, we will see a very important theorem, which is Green's theorem. It connects actually line integrals with double integrals. So thank you and goodbye till then.